Good. I'm really happy to be here. It's wonderful to be here in Milan and a very exciting conference. I really appreciate the invitation to speak. And what I'd really like to talk to you about today is how we are all, as individuals, as researchers, and as representatives from a variety of different businesses and industries, dealing with unprecedented change and how we can navigate within that to be successful. And there are many challenges ahead, but there's also a tremendous amount of opportunity that comes with change, and I think it's a very exciting opportunity that we all can collaborate and help to address, solve, and really open up some new opportunities for us all. So to put this in context, let's make sure we are moving forward. There we go. I wanted to just first describe some of the particular challenges that are facing industry and business. They're really in three main regimes: the market, the competitive, and the technology challenges. There's massive disruption. You know this, we see this and hear this every day. From the market perspective, let's see if I can get that. From the market perspective, we see a change coming from globalization, regulatory changes and shifts which are affecting so many different industries, security concerns and more, which is putting tremendous pressure on businesses in every industry. At the same time, we know it's not enough just to survive. We want to thrive. We want to compete in a very competitive world in which new players as well as incumbents are coming at the challenges in different ways, and it's really putting a whole new set of pressures on those individual businesses. And what I'll spend more time on today are those technologies, those technology inflection points, which are also posing challenges, but at the same time some opportunities. At IBM, we talk about something called cognitive enterprises, and really what we mean by that is the journey that all businesses are on to incorporate these new technologies to truly become intelligent, automated, and agile. And there are many elements of this stack that you can read here, but it really starts at the top with embedding agility into everything we do, into our business processes, into the roles, the skills, and the tasks. Really empowering an ecosystem around all these different industry and market partners, new workflows, and the incorporation of these new technologies to make a difference for the business. On top of massive amounts of data, structured data, unstructured data coming from mobile internet traffic for everything what we do. We know that that's just generating tremendous opportunity for new insights, but also a security risk and a challenge for managing and proactively acting on the insights from that data. And on top of that, the infrastructure, the changes in the infrastructure and the move to cloud, private, on-prem, off-prem, public, and multi-cloud environments, which are all presenting, again, opportunities and challenges. Every business is on a journey towards a cognitive enterprise solution. Many of us are actually very early days in that journey, but the opportunity is ahead of us to incorporate many of these capabilities to enhance what we do and how we do it. At the very same time, technology shifts are accelerating. Now, we've all seen over decades new technologies evolve, mature, and become available. I think we can all probably recognize that over this past decade and even very much today, those new technologies are coming at an ever-increasing pace. And the challenge is, how do we deal with it? How can we respond, be proactive? And there is a first mover advantage. So those businesses that can take advantage of the new technology have a tremendous competitive differentiation opportunity in the marketplace. And so it's on everyone's best interest to figure out how and what to do with these new technologies to make it really make a difference in the very specific industries and use cases that we're challenged with. So given that, and given that complexity and the challenge that we're all facing, I thought I would put this into a context of a vision for where that technology is going, and how putting our head around that vision, getting a better idea of where the technology and how it will evolve, will give us all a bit better grounding and understanding of how we can then anticipate and respond to apply that in different businesses and industries. And the story and the vision that I'll tell you is one for how computing will evolve. What does the future of computing look like? And I'll suggest to you that the future of computing will be very different than the computing of the past. And this is a story of bits plus neurons plus qubits. And during the next 20, 30 minutes or so, I hope that you understand what I mean by all that. So the story begins with the combination of mathematics and information that really formed the basis of the computing that we know today. And it's a story we'll call the Shannon story, named after Claude Shannon, who is known as one of the fathers of information theory, classical information theory. And Claude Shannon really taught us that it's possible to encode information very simply into bits, binary digits of 0 and 1. It's a concept we take for granted today, but it really formed the basis of what has become all the digitization of technology today. And it is what has allowed us to scale and encode information and build up computing power that is so powerful today and has transformed every business and every industry. And this simple concept allowed us to take information and encode it in a consistent way, whether that information was in a classical punch card or even held the information in our DNA. We know that today, right? We know that you can take images and video and data and speech, and we say all of that information can be encoded in bits of 0 and 1. But it actually is a pretty radical concept that both of these things are actually the same when it can be digitized in a very simple way. That fundamental concept has led to amazing advancements supported by the progress that we know as Moore's Law. So very simply speaking, the last 40, 50, even 60 years of evolution in computing technology can be described by a prediction that Gordon Moore from Intel made that said we would about double the number of transistors that we could capture on integrated circuit chips about every 2 years. And those transistors are the switches that can allow us to switch from 0 and 1s, these bits. And the fact that you could pack more and more and more bits together and increase those in an exponential fashion has led to the digitization of the world. We know that, right? Look at the massive, massive amounts of data. And this statistic is astounding to me. By 2025, I expect that there are about 175 zettabytes of data created, captured, or replicated annually. A zettabyte of data is 10 to the 21st bytes. It's just a crazy number. We can't even get our head around it, right? And you see some of this specific statistics on the numbers of terabytes, petabytes, exabytes, zettabytes that are created, stored for all these different types of mobile internet and other applications. The fact that there are these massive amounts of data available has just enabled tremendous opportunity, right? The fact that this is digitized means we can now analyze, predict, optimize, and do a tremendous amount of insight for a variety of applications. It also poses challenges because all that data has a risk of being tampered with or having security breaches. And we know this is happening at an ever-increasing pace. Draw you to one number that almost 15 billion records have been breached since 2013. And the overall cost of a single data breach is nearly $4 million. Again, these are kind of scary numbers for those of us in industries in which the protection of data is paramount. And frankly, we're all in industries in which the protection of data is paramount, whether you're in healthcare or financial services or IT or education. The protection of personal, sensitive, financial, health records, all of that It's a concern that we all have, and obviously it's something that we need to take very, very seriously. So the evolution, the digitization of everything, more and more bits driven by the progress with Moore's Law. This is an example of the state-of-the-art bits system. So the latest mainframe technology, this is a picture of the Z14 system, is actually the most reliable, scalable, secure bit system in the world today. In a Z14 system, we can process 850 million encryption transactions per day. A single chip, it's about the size of my fingernail, has over 6 billion transistors on it. Those transistors are switching at incredible speed that allows us to drive this level of processing power to power the back offices of banks, retail institutions, travel and transportation industry, and more. What's so critical here is it also has the highest levels of industry security and data protection, which is not something that can be bolted on as an afterthought, but really needs to be built in from the ground up. That bit story, that's been the entire story of the history of computing. It's a complicated story. We're continuing to evolve it, and we will continue to increase the bit speed, density, new materials, new device structures, new applications, new security solutions. We will for sure continue on that path. But that's not the whole story, and that will not be the entire story of the future of computing. A second piece of the puzzle is how we incorporate new learning systems, or AI systems, into the computing fabric. And this is really inspired by our understanding of how the brain works. So this is a story we call the Ramon y Cajal story, which is named after a man from Spain who first studied the brain. And you see here a pen and ink drawing made in 1899, so just around the turn of the century. It was the first time that we really understood that within our brain we have neurons connected by synapses, and that the way our brain works is actually very different than the way we've designed these traditional bit-based classical computing systems. Bit-based systems are programmed, they're very deliberate, they're repeatable, and that's great for a variety of applications. Our brain is an extraordinary system that we don't even understand well today. Our brain's a very good low-power processor. It does parallel processing very efficiently. It learns based on experiences and data, and it reasons. And those attributes have inspired a whole new set of computing capabilities that we today know as AI systems. In the 1940s, quite some time ago, was when we first started to instantiate the artificial neural network. So inspired by the brain, we said, is there something we can design artificially that would replicate the concept of neurons and synapses and learning, but do that in an artificial way? And again, this was well before the artificial computers, AI computers that we know and love today. So the concept, and what you see here is an example of a neural network architecture. Every one of these dots is essentially a neuron, and they're connected by lines which are artificial synapses. They're the connections between these neurons. And the concept here, and what's been applied so actively in the last several decades, is to be able to create systems based on this artificial neural network architecture that can be trained based on large amounts of available data, and then can learn based on that data and create outputs that are not pre-programmed based on rules, but are now derived based on the learning from the data. And so the training data then would result in weights, so an amount of weight for each of those connections, and that gets more and more accurate depending on the amount and the quality of that data that's been used to train. As an example, we've trained this based on images to recognize a cat versus a dog, which is always the simplest AI example. Here you put a cat in, and if the training has been done effectively, you can very, very accurately have an output that determines this is a cat. Well, just in the last decade, we have seen that concept now take root and see tremendous advantages in performance, reliability, and accuracy. Why? Well, we've seen the confluence. This is a new concept, right? In the 1940s, we had artificial neural networks, so why now? Well, the confluence of those large amounts of data sets for training, combined with new algorithms and optimized solutions for performing those AI capabilities, and the computing infrastructure that has advanced to enable the acceleration of the training to make it really viable in reasonable amounts of time, has enabled this massive acceleration in the AI world in just the very recent years. What you see is, interestingly, 2012 was when the accelerator chips, so the graphics processing units or GPUs that are used to greatly speed the training of the AI models, when those were first used, for an example, in this case it was the ImageNet classification task, large amounts of images, how quickly and accurately could the machine identify what was the content classification of an image. So in 2012, we first applied the deep neural network, multi-layer neural network solutions, combined with graphics processing units as accelerators, and over the coming years saw a massive improvement, a reduction in error of the classifications, and for the first time in 2015, so only a few years ago, actually had the accuracy better from an artificial system than from a human. So this is where we are today. We have farther than that, but we now have an opportunity to take advantage of systems that learn for many, many applications. So where are we with the evolution of AI? I argue that we're still actually pretty early days. So AI, as we've all seen it applied in many consumer applications for facial recognition, for voice to text, for language translation, and more, those are typically what we call narrow AI solutions. That's AI applied to a very particular task in a very particular domain, and it works extremely well. We can apply AI with superhuman accuracy in those kind of applications. But we have a long way ahead of us, and for many of the commercial and enterprise type applications, there's still quite a work we have to do to make AI ready, scalable, robust, trusted, and explainable for those enterprise applications. So we define this area in blue in the middle that we call broad AI, and that's the era that we're really just at the beginning of, and what we see as really critical for the application in enterprise environments. Just briefly mention that lots of talk about general AI, about autonomous AI systems that can think and reason for us. It's our expectation that we're still decades away from the science fiction view of AI, but we have a lot of opportunity in the next decades to apply AI to many compelling applications, and I'll describe to you some of the advances that are required to get there. Just a few statistics on AI adoption. Everybody believes fundamentally that AI will be transformative across industries, but only about 1 in 20 companies have extensively incorporated AI. So we have a long way to go, and I'll tell you some of the key inhibitors on why we've not adopted it more broadly. So number one is that there are more capabilities in terms of trust and explainability that are required. Active areas of research today in both universities and in corporate environments. Lots of progress that's being made, rapid pace, more work to do, making sure that the AI technology is secure. With every new technology, just as we can take advantage of it, we can also see it being used for bad. So AI models are being attacked, AI data needs to be secure, AI algorithms must be trusted. So we have technology solutions to make those possible, and more research and development that's required to roll those out more broadly. Explainability is a key inhibitor, especially in applications in regulated environments. So, if you're wanting to apply AI in a healthcare solution, it's not reasonable to simply have an output that's black or white that says, yes, this is malignant, or no, it's not. Yes, you qualify, no, you're not. Clearly, we need more explanation that goes with that. Why? What's the level of confidence based on what prior data, what similarities, a clear and definitive and explanatory explanations so that both the individual, the end user, the patient in this case, and doctor, the payer, the insurance environment, all are going to require an explanation. And there is, again, technology required to make that explainability transparent for all different applications. There's also progress that's required on the compute requirements for the broad AI era. So as we want AI to be able to move from task to task and domain to domain, to be scalable for many applications, that underlying infrastructure needs to support it. I mentioned the graphics processing units, or GPUs. It's been a tremendous opportunity for us to take advantage of GPUs that were really created for gaming systems and apply them to AI. What a nice coincidence that it works so well. Well, you can imagine that if we design hardware accelerators specifically for AI, we can do even better. And there are tremendous opportunities to optimize the hardware infrastructure for AI acceleration. And there is some very active work on approximate computing as a way to even further enhance our ability to do AI in memory computing, as well as analog is coming back. We all have seen analog of the past. Analog technology may hold some very exciting opportunities for AI acceleration of the future. So we have two pieces of the pie, the evolution of the bit story and the AI system story. And I'd argue that those are already being combined in sophisticated ways. Here's an example of the most powerful bits plus neurons system available today. This is the Summit supercomputer. It's the fastest supercomputer in the world. It was developed in collaboration with the US National Labs and has been being deployed today for some very interesting, challenging applications. What you see inside the Summit machine is over 9,000 traditional bit processors and over 27,000 GPUs, or AI accelerators. That's a lot. It's a lot of hardware in there. And it's the combination of those technologies that really allow the system to fly. The system can run over 200,000 trillion calculations per second, or 200 petaflops. Now, if that wasn't enough, there's a third piece of that pie, and this is the evolution of the quantum story. And I'll tell you, as someone who studied applied physics in school, I did not expect that in my lifetime we would be able to have real live quantum computers available through the web to be able to run applications for business, for science and industry. But we can, and we see in the very foreseeable future that the evolution of this technology will be available for solving some problems that are intractable by other means. This is a story about combining physics with information, and Ralph Landauer and Charlie Bennett were some of the early innovators in this space, and we've seen tremendous progress just in the past decade. We talked about the bit, the 0 and the 1, and the simplicity with which we can now digitize information. Well, it gets more complicated when we talk about quantum. Nature is quantum, it's quantum mechanical, and so it actually is very applicable to many of the really fundamental physical questions that we have. Within quantum, a quantum bit, or what we call a qubit, is not just a 0 or 1, but also can have the superposition of the two. And as a result, we have this massive state space that we can now calculate or simulate over. That state space goes as 2 to the power n, where n is those number of qubits. So if you have 2 qubits, 2 to the 2 is 4, okay, small. 10 qubits, 2 to the 10, we know it's 1,024, it's getting interesting. 50 qubits, which is about the size of the largest quantum computer that has been demonstrated today. Well, now, it's pretty interesting, 2 to the 50th, it's about a quadrillion. So it gets interesting really fast, and the continued evolution of the hardware technology, the algorithms and support are making today a really interesting time to be in the field of quantum. What you see here is a picture of one of our laboratories in New York with quantum computing evolution. Just in the last several years, we have made the quantum computers publicly available on the web. You can get access on the IBM Q Experience and run some free tests. There's a simulator, and there's actual real quantum hardware that you can run experiments on. And actually, many, many people do run experiments on these. Our academic partners, working with the startup community and with corporates in industries from financial services through oil and gas and many others, are interested in exploring what quantum can do because it offers tremendous promise. and a potential competitive advantage. Earlier this year, we introduced a system called System 1. This is the first industrial design quantum computer. This is a quantum computer designed for business. It's not an experimental lab like you saw on the prior chart. It's actually a system that is intended to scale. It has an industrial design with a separate cooling mechanism, a separate electronic system, vibration control, everything that you would have in a traditional scalable system that operates at 15 millikelvin. So there's some unique aspects. Since we don't expect our clients to want to run and support those kind of unique requirements, we make this available in a secure way through cloud connections. And that's an incredibly powerful technique for those who want to experiment with this, but may not have all of the skills for every aspect of building quantum computers. So what's the future of the quantum world? Just as we had a prediction by Gordon Moore that traditional classical computing would scale in an exponential fashion, and it did, we actually have a prediction that we'll see a similar exponential progress on the quantum side. We only have a few data points, but frankly, Gordon Moore only had a few data points when he made his prediction as well. The key metric in quantum is something we call quantum volume. Quantum volume is a metric that combines the number of qubits with the quality of those qubits. So number alone doesn't tell you much, but if the error rate and the quality of those qubits are good, then the quantum volume is a metric about how much capability and how much work can you do on a quantum computer. And it's our prediction that quantum volume will double almost every year going forward into the future. At that rate and pace, there is much ahead of us in just the coming years that can be done with the evolution of this quantum computer. Been a lot of progress just in the last few years. I'm sure some of you have seen, many of you have probably worked in this area, so it's an area that's ripe with innovation, lots of publications, lots of exciting results in the areas of using quantum to simulate quantum nature, right? So areas like quantum chemistry, material science, and high energy physics are ripe for the application of quantum computing. It's actually a really interesting area as we combine quantum and AI. AI to help with quantum, and quantum to help with AI, and we do see the ability for quantum to improve machine learning. And finally, the area of optimization. Applying quantum to optimization solutions has a tremendous promise and some early applications that we're exploring. But as I said, with every new technology, we also have concerns about its misuse. So interestingly, as the quantum computing systems and the quantum volume evolve, we expect it to make most traditionally used cryptography solutions obsolete. That means it can break RSA cryptography, which is a risk. It's a risk that many of us are concerned about. So there are new cryptography solutions that are robust or safe against the large-scale fault-tolerant quantum computers of the future. Lattice cryptography is one of those solutions. Oh, sorry, maybe the animation happened and went away. Lattice cryptography is one of those solutions. What that does is it hides the crypto keys in a large n-dimensional lattice, and it is robust even in the advent of very, very, very large-scale quantum computers. That capability exists today, but it's not too early to apply it. So data that we have stored, even encrypted today, though we don't have quantum computers that can break that encryption yet, imagine you put that data stored in a large database. Imagine hackers get access to that database. They can't make sense of it today. But a few years from now, when those quantum computers are available, they could potentially decrypt that. And so the opportunity to apply some of these new cryptographic solutions like lattice cryptography, it's not too soon, and in fact, we all need to be really diligent in applying new technologies quickly so that we can make sure that the data that we've kept safe continues to be secure. So we talked about those three pieces of the pie: the evolution of the bit story, the AI systems, and the quantum. And it's our point of view that it's going to be the combination of those technologies that forms the computational foundation for the future of computing. But that's not enough. So it's really going to be, how do we take advantage of that technology? And the evolution of hybrid cloud will be required to simplify that complexity, to be able to manage and deploy workloads over that infrastructure. So we think about the evolution of hybrid cloud on 3 different dimensions. The first is the specialization of computation. We're moving from a very homogeneous environment to one that's going to be diverse. Quantum computing will have solutions like these hardware accelerators and more, and we need to be able to take advantage of those different computational capabilities for specific workloads, use cases, and applications. Second, computing localization, moving from a centralized cloud infrastructure to one that is not all in one place. Maybe it's multi-cloud, certainly a strong point of view that IBM advocates for multiple public, private, hybrid solutions. Moving out to the edge, we all see computational power becoming more important in edge environments, and that localization, specialization is a change that we need to acknowledge and support. And finally, the changes in the application development process, moving from truly monolithic large-scale applications to one that is much more in the microservices-oriented architecture that makes a tremendous opportunity for composing new applications. It's changing the way we design and architect solutions, and it's putting pressure on how do we integrate with legacy systems. All of these changes are really driving a massive set of new requirements for hybrid cloud. Our expectation that hybrid is here to stay. It is not a point along a journey towards some future nirvana where everything's in one place, but it's actually our expectation that hybrid multi-cloud is the future. The one statistic I'll call out to you on this page is that although only 20% has already moved to the cloud, the opportunity is in front of us. 80% of enterprise workloads still have an opportunity to move to some sort of cloud deployment solutions. That means there's actually still a lot of work to do. Those applications that have already moved are the easy ones. Those are ones that were lift and shift, move to the cloud. The remaining will require some sophistication and some consideration about how best to parse and distribute and manage those applications in the hybrid environment. Many of you may have seen the news that just yesterday, IBM announced the formal approval of the acquisition of Red Hat. So this is a big deal for IBM and for Red Hat, and it is our very strong point of view that hybrid cloud means open, it means choice, it means that businesses and clients everywhere will have lots of selection choice in where and how they deploy their workloads. And it's every conversation with every client confirms for me that we need to make sure that choice is preserved. So using different public cloud vendors, being able to preserve some on-premise private cloud environments, being able to manage moving workload from place to place. The solution to enable that is a container-based infrastructure that allows you to be mobile and to be able to transport workload in a seamless way across different environments. Because of the complexity of the infrastructure, of the software environment, and the stack that we just talked about, it is imperative now more than ever that we have a degree of automation to do everything we're doing, particularly around the programming space. Imagine if we all tried to do everything here manually and in traditional ways. It's not viable given the scale and the size of data resources, of amount of code that's being developed. You see here a few statistics. There simply aren't enough data scientists and software engineers in the world today to satisfy the requirements around code generation. There's a couple of US numbers, but even globally, the demand for data scientists is growing. It's great if you're a student right now. It's a good market out there. It's not so great if you're an employer because you're probably fighting for that talent. We know that there's a resource gap. So one, we can encourage people to study and get into this field, and we for sure should do that. And we need to apply technology to automate the production of code. We see tremendous opportunity there. It improves not just our ability to be efficient in code generation, but also to improve quality. Right? If you can reuse components of code, compose compose programs automatically or even derive them from first principles. We have an ability to improve the quality of that code. And today, over 50% of developer time is spent debugging code. Wouldn't we want to use those important resources really to create new? Give you one example of automation. It's actually applying AI to AI, right? We want to use AI to improve the way that we design, optimize, and govern the AI itself. And you're seeing here an example of an optimized neural network produced using a system that's known as NewNet, or it's a neural network synthesis solution. So typically, we would use AI experts to optimize every element of that artificial neural network. So we have the right number of layers, the right design, lots of different considerations, and you need deep expertise to do that and do that well. Well, we can automate much of that, and that will allow us to speed the use and the deployment of AI for many applications. So I talked about a future of computing in which the bits, the AI, and the quantum, so bits, neurons, and qubits, come together to form the basis for a new computing infrastructure managed by the evolution of the hybrid cloud fabric, supported by automation and AI. What do you do with all that? Well, it's our expectation that that is actually what will power the next generation of mission-critical applications across many, many industries, as well as enable fundamental new ways of science and discovery. Let me show you some examples. I believe that the future of computing will enable the future of healthcare, agriculture, manufacturing, financial services, and even fundamentally discovery. You know, I'll give you some of these examples that I just find really compelling. There are many, many more. In the healthcare space, the ability to apply that future of computing vision to transform diagnostics, to improve outcomes for patients, there's probably not a more compelling application that anybody in the world can imagine. And we're starting to see the fruits of those capabilities be applied, and I think the promise is even greater. We look at genomics, genomic medicine, been really, really good progress. The ability to automatically sequence the genome can be done more efficiently now than ever before. That opens up a lot of opportunity. And there's a bunch of challenges still left. Massive amounts of data privacy concerns are paramount in this space. Being able to integrate different types of solutions, to use AI to identify similarities and improve our ability to select the appropriate treatment for patients so that we can get the right treatment first. All of this is before us. I think there's some really good progress that's been made. Even applying high-performance computing, accelerated AI to understanding of new treatment solutions, immunotherapies, been very, very good progress that's been made just in the past year. Imagine all of the images when we go to the doctor and we get an MRI or a mammogram or a CT scan. There's massive amounts of image information that's captured in the medical environment that we frankly don't take advantage of. So using automatic systems for extracting information from the large amounts of image information combined with text, whether those medical tests or medical records that are digitized, we can actually accelerate the identification of anomalies in these images, as well as guide the experts, the doctors and those who can, radiologists, who can help identify the right treatment options. So it's always our point of view that we're looking at technology as augmenting the experts in the field, but how can we do that in the most effective way? And here's some examples of applying the technologies that are available today and that are coming to really accelerating the image analytics in the healthcare space. In manufacturing, there are a whole set of very exciting application areas, optimization for production, for worker safety, and more. If you think about it, in a modern manufacturing facility, there are hundreds of thousands of sensors that are collecting real-time data. That data gives us insights into the performance on the manufacturing line that, if looked over time, can help us to predict anomalies and failures, and if reacted to, can allow us to optimize the production itself. Now, we need to do that, right? So we've been taking the data for some time, so those technologies are now becoming available to be able to optimize and really radically change and improve the ability to manufacture in all different industries. So think about aluminum smelter pots, semiconductor manufacturing, in mining and more. The ability to optimize production, to be able to reduce waste, to be able to improve the safety of individuals working on the manufacturing line. And there's a tremendous opportunity, very high value proposition here, and we're already seeing some of these technologies applied here, and more opportunity to come. Agriculture, one of those industries everywhere in the world, and so many different value points along the ecosystem chain, whether the farmer themselves, the suppliers, the retail supply chain solutions, the financial institutions. Everyone in that value chain has tremendous to gain from efficiencies that we can gain by applying advanced technologies, that future of computing vision, to the agricultural space. As an example, we can monitor crop health using satellite imagery, applying AI parsing of those images to look for anomalies, to detect the accuracy of the soil moisture and optimize to improve yields. We can detect diseases early to be able to have better intervention, improve yields, to be able to manage the supply chain and optimize our production. All of those are really exciting examples and already beginning, and I think there's lots of opportunity ahead. In the financial space, and we're going to have a panel shortly, and this will be a topic of some discussion today, we think there are many applications in financial services where these advanced computing technologies will be very powerful. The first is in the area of financial crimes, tremendous area of concern, whether it's detecting fraud, money laundering, and more, applying graph-powered machine learning, leveraging some of these advanced AI underlying technologies and high-performance computing, the advanced bit systems. Those come together to allow us to reduce the number of false positives from a financial crime analysis and to be able to improve the accuracy. Applying the deep learning solutions to credit card fraud, credit card risk calculations. There's a real opportunity here. Every financial institution would make a risk calculation based on a traditional rules-based technique, and that can be improved, accelerated, and accuracy can be enhanced by applying AI, deep learning, and acceleration technology to bear on this problem. And now we can apply quantum as well. So the ability to now combine quantum technologies with our AI and our bit systems are starting to become real. And I'll show you just two examples here. Applying a quantum computing technology to pricing and risk analytics in financial services. It's a really exciting opportunity. We know traditional methods, we would use Monte Carlo methods. We get a quadratic speed up using quantum computing. Well, we're still early days, but I think there's a really exciting opportunity. And you imagine using quantum computing to optimize your financial portfolio. Well, everybody's working on financial portfolio analysis. We use traditional computing methods. We try to apply AI. And now I believe quantum computing will be revolutionary in this space as well. And as we increase the quantum volume, we continue on that roadmap, we develop more sophisticated algorithms. There's a real exciting opportunity here. And the last example I'll leave with you is how I believe the future of computing will really change the way we do science and discovery and R&D. And as someone in the research realm, I think that's really exciting. It's like eating your own cooking. It's applying the technology to what we do every day. Science and the process of discovery is, it's fairly ad hoc. I mean, yes, we have the scientific method, but we rely on really smart people to design the right experiments, to perform them well, and to make sense of those results. Imagine imagine if we could better select the right experiments, if we could vet from all of the possible things that we could choose to do in a laboratory and apply our skills to those that would be the most promising. We believe we can really accelerate the discovery process, whether you're looking at new materials, new algorithms, solutions across many, many different industries. We believe the combination of that infrastructure evolution, the bits, the neurons, and the qubits, combined with our ability to manage over those with hybrid cloud, with automation, will radically transform our process of discovery, accelerating it, and really enabling us to improve outcomes. Okay, with that, I will close and happy to take any questions if you have them. Thank you.